This is a somewhat tongue-in-cheek look at Santa, because somebody asked me many years ago, can Santa exist? Which shocked me to the core that anybody would actually ask that question. But I thought, well, what does science have to say about Santa? Is Santa compatible with the laws of physics? As a physicist, this is something dear to my heart. So how many laws of physics does he actually break is the question. Allegedly, according to folklore, Santa is a portly, jolly fellow with a white beard and a penchant for wearing red suits. Now, despite having a questionable fashion sense, that doesn't necessarily mean he can't exist. And what about the claims that are made? There are lots of claims about what Santa does around Christmas time. He allegedly visits all households on Christmas Eve to deliver presents to all qualifying children. And qualifying children, of course, depends on the naughty nice list. So can we reconcile the fact that he visits all children on Christmas Eve? Can we reconcile that with our understanding of science? And at the time I thought, well, I've actually given quite a few talks that are astronomy related. I wonder, is anything that I've ever said about science, in terms of talking about physics, talking about astronomy, talking about the way the universe works, is there anything I've ever said in any of my talks that help us understand whether or not Santa does or does not exist? So I thought, yeah, okay, let's actually do that then. Let's take the statement. This is the statement we're going to question. Is that actually reasonable, that Santa visits households on Christmas Eve to deliver presents to children? Can we sort of deconstruct that one word at a time and work out, is there any aspect of that that actually violates any laws of physics? And if so, how many laws of physics are violated? So we'll deal with that one step at a time. First, we'll ask ourselves, how many children does he have to actually visit? Okay, there are something like 8 billion people in the world. That's a bit scary, isn't it? But that's the fact. There are 8 billion people, and amazingly, 25% of them are children. That surprised me, but of course, that's just an indication of the birth rate at the moment. 50% are eligible for Christmas presents. That's just an estimate. You could argue, well, does Santa give presents to anybody other than children in Christian families? Well, generally speaking, yes. He is not so mean as to say, well, you're not Christian, therefore Father Christmas doesn't apply to you. So I reckon about 1 billion children are eligible for Christmas presents. That assumes they're all on the nice list. If you assume that 99% of them are on the naughty list, the numbers go down considerably. But let's assume they're all nice. And let's assume that everybody eligible gets a Christmas present regardless of their family's main religion, in a sense. So we've got 1 billion people to deal with. And Santa visits them. Okay, so let's think about how Santa visits 1 billion people in a night. How does he get there? Well, he gets there on a sleigh pulled by flying reindeer. So the first question is, can reindeer fly? Okay, a very sensible question. We know that insects fly. We know that birds fly. We know that pterosaurs and pterodactyls fly. You don't see many of them these days, but apparently they do. And of course, some mammals fly as well. There are a number of different mammals that can fly. What about reindeer? Well, if reindeer can fly, they clearly choose not to do so for most of the time, because nobody's actually caught a photograph of a reindeer flying. So there's very little evidence, essentially no evidence, for flying reindeer. But as a scientist, you have to remember that absence of evidence is not evidence of absence. Just because you haven't got a photograph of a reindeer flying doesn't mean they can't fly. It just means that you've never caught one that was flying, you've never been around with a camera. So the jury is out. There is no proof for or against the idea that reindeer can fly. So let's assume they can for the time being, because we can't prove otherwise. How fast would you have to go in order to do this on Christmas Eve? Well, to visit 1 billion children in one night, let's assume that's about 36 hours. It's not 12 hours because you can use the rotation of the Earth. If you visit the time zones in the right order, you have approximately 36 hours to do your visitations, as it were. If you work out the minimum speed he would have to go in order to visit everybody, it depends how they're arranged on Earth. Are they all uniformly spread over the Earth? Well, no, because they're often clustered in big cities, etc. We have to make some assumptions. But you can say that he would have to go at a minimum of 2,000 kilometers per second, which sounds really fast. No, it isn't. It's a tiny, tiny fraction of the speed of light. And in a separate talk, I talk about measuring the speed of light. I measure the speed of light using a microwave oven and show that the speed of light is 300,000 kilometers per second. So this speed is tiny. It's not even 1% of the speed of light. Santa is nowhere near breaking the physics speed limit. So we know that no object can travel faster than the speed of light in a vacuum. The universe is actually expanding, and the universe is expanding faster than that, but that's a different situation. Santa moving across the face of the Earth at 0.07 of the speed of light is nowhere close to breaking any physics rules or any physics laws. But if he did move really fast, wouldn't you have roast reindeer? Because of the it's not actually friction, that's a misnomer. Whenever an object like an asteroid comes hurtling through the Earth's atmosphere, it's not friction that heats it up, it's the compression of air in front of the asteroid or the comet, whatever it is. Same for a little meteor, a tiny little grain of sand, it will be compressing the air in front of it and hence heating things up. So if you compress the air in front of the sleigh, it will heat up, and surely that means that you're going to end up with a very visible Santa and sleigh and reindeer. So in a separate talk about the evolution of stars, the ABC of how stars evolve, the ABC of stellar evolution, the A and the B and the C stand for particular things, and the C stands for compression. That's why stars get hot, because they are compressed. And so compression produces heat. So we know that even with an aerodynamic sleigh, even if you try and make it as aerodynamic as possible, it's still going to heat up. So doesn't that mean that the Santa and sleigh are going to be white hot as they go backwards and forwards across the Earth visiting all of these people? So why don't we see an absolute bright supernova crisscrossing the sky on Christmas Eve? If we know that compression produces heat and we know that hot objects glow, especially when they're really hot, then it ought to be easily visible. We ought to see a bright light on the sky around Christmas time. And you could argue, well, maybe we didn't. But it's a bit of a push to say, well, actually, the Star of Bethlehem was Santa, because that means Santa existed before the birth of Christ, and that doesn't seem to quite ring true somehow. So you could say, well, it probably wasn't the Star of Bethlehem, but bright lights in the sky? Well, yes, there's plenty of people who see UFOs and claim to see bright lights, but they see them all year round, not just on Christmas Eve. So that doesn't seem to fit either. So again, regarding the sleigh glowing white hot because of the speed at which he moves, is there anything that gets round this problem? Well, there is, because when you say this object that's moving really fast, whether it be the sleigh or the reindeer or anything else, are going to get really hot and therefore they're going to glow, well, that doesn't apply to all matter. It applies to the sort of matter that we're used to. Take a lump of pretty much anything, heat it up, eventually it gets red hot, eventually it gets white hot. But it doesn't apply to certain bits of the universe. Some of the universe is made of dark matter. Dark matter does not glow when it gets hot. Dark matter, as its name suggests, is always dark. Strictly speaking, it's more invisible matter. It can't be seen. It doesn't absorb light. It doesn't emit light. So dark matter, we think, A, exists, and B, we think a lot of the universe is made of dark matter. There appears to be more dark matter out there somewhere than there is ordinary matter that makes up you and me and the Earth and the trees and the mountains and everything else. So maybe the explanation is, well, okay, that's fine then. If Santa and his sleigh and reindeer are made of dark matter, not ordinary matter, that explains why they don't glow, even if they are getting quite hot. Okay, it also explains why the sleigh doesn't show up on radar, because it doesn't emit or reflect any radar. Hence, you don't actually see it in terms of a little blip going across the globe on Christmas Eve. Okay. Right, so we've had children, we've had visits. What about households? He's going to visit all these households and somehow gain entry and leave gifts for the children. So how does he get down so many chimneys? Remember, he's a rather portly fellow. Chimneys, generally speaking, are not very large diameter orifices. So how is he going to squeeze down what is necessary, which is about 3,000 chimneys per second. Now, that's quite fast for anybody. It is very fast for a portly gentleman. That's not necessarily a problem, because there are laws of physics that say, and here we're talking about laws of physics on a very small scale. In the weird world of the very, very small, I describe how the laws of physics on tiny scales, so-called quantum mechanics, quantum scales, tell us that, well, an atom is made of a nucleus with loads of electrons going around of it, and of course we are made of molecules which are made of atoms, and hence we have a particular size. But if you were to somehow, I don't know how, but if you were to somehow replace all of the electrons in an atom with a different fundamental particle, it's a particle called a muon. It doesn't matter about the nature of this particle, it's simply an existing particle that we know about. If you could swap the electrons for muons, then atoms would become much smaller, by a factor of about 200. So that would happen for all the atoms in Santa. So instead of Santa being 2 meters tall, he would be about 1 centimeter tall, and hence would drop down a chimney no problem whatsoever. But you could say, well, that's a cheat. What if you haven't got a chimney? There's a lot of houses these days that don't have chimneys. So how is he going to get inside the building if there's no chimney for him to fall down, even if he's only 1 centimeter or so in size? Well, quantum mechanics comes to the rescue again, because quantum mechanics tells us if you're outside a room and you want to be inside a room, you don't have to go through the doors or the windows. You can so-called tunnel. This means not bashing the wall down until there's a gap there and going through. It's a quantum mechanical phenomena which we know happens because it explains lots of phenomena in physics, that an object can basically appear somewhere where, according to good old-fashioned Newtonian mechanics, good old-fashioned classical physics, it shouldn't happen. It is possible for a particle to appear, for instance, inside a room, even though it didn't come through an open window or an open door or a tiny gap in the brickwork. It is possible to tunnel in the quantum mechanical sense through a region which, in principle, it shouldn't, according to old-fashioned physics. This is something we've learnt in the last few decades. So it's possible, if a particle can do that, why can't Santa tunnel his way from the outside of a building to the inside of a building without going through any open door or open window? So, yep, there's no reason why he can't do that. I don't know how he would do that, but it doesn't disobey any laws of physics. Right, so we've done children, we've done visits, we've done households. He does this on Christmas Eve. So all in one night. Somehow he does all of this in one night. How can he make so many deliveries all in 36 hours? Remember, that's the time limit that we're working to. Well, again, quantum mechanics, isn't quantum mechanics wonderful? It comes to our rescue yet again. In quantum mechanics, when we look at the subatomic world and what nuclei and electrons and atoms are doing, when we look at the properties of atoms, we find, well, actually, they can be in 2 places at once. That makes no sense in terms of common sense, but common sense is based on us looking at the world on a scale of centimeters and meters and kilometers. When we look at the world on a tiny scale of atoms, we find things behave differently. And it is possible for an electron to be in 2 places at once. It's possible for an atom to be in 2 places at once. And so if it's possible for subatomic particles to be in 2 places at once, why can't Santa? All you have to do is to say, well, you just have to scale it up. Again, I don't know how he achieves that, but if we assume that he's using this subatomic rule, this subatomic law, then maybe it's okay. Now, you might say, I don't like that idea of being in 2 places at once. Then you need an alternative way to make the deliveries. Well, I don't think it breaks any rules, but there is an alternative if you don't like the idea of Santa being in more than one place at one time. Because space itself, that we think of as just the empty gaps between stars, space can be distorted by the presence of matter. Studies of, for instance, black holes and other stars have told us that the existence of a heavy star like a neutron star or a black hole actually changes and distorts the space around it. It actually distorts time as well. But here we're just interested in distortions of space. So in other words, Santa can change space to make it such that he doesn't have to travel quite as far. He simply arranges it so that space is a little bit compressed, making it easier to get from one place to another. Right, so we've had children, we've had visits, we've had households, we've had it's all done on Christmas Eve, but he's got to do this with all the presents in tow. And remember, we've got 1 billion presents here, assuming no kids are going to share. So, Santa's sack. How can Santa carry all of the presents that he needs to take with them? So we're talking about one present for each of 1 billion children. So how can the sleigh possibly hold 1 billion presents? Even if the presents are quite small, that's an awful lot of a sack for the sleigh to carry. Well, one solution is coming back to the idea of black holes and neutron stars. They can distort space and they can distort time. Black holes in particular distort space in such a way that you get this rather weird result that black holes are actually bigger on the inside than they are on the outside. That sounds really weird, but then black holes are really weird. Just like atoms are weird when you look at them on small scales, so black holes are weird because you've got an awful lot of mass in a small space, and they make such a distortion, such a warping of space and time that you get really odd results. So black holes are bigger on the inside than they are on the outside, so why can't the sleigh do the same thing? Again, Santa has to be able to manipulate space and time, but maybe he can. And if the sleigh is bigger on the inside than it is on the outside, then all you have to do is to make sure it's big enough to take all of those 1 billion presents. Even though on the outside, it still looks as small as you would expect. Now, there is actually an alternative. Again, there's a different way of getting around this problem. We think we live in a universe of 3 dimensions, forward, backward, left, right, up, down. There are plenty of people who think, no, there are actually more dimensions than that, but we can only see 3 dimensions because that's the limitation of our brains, that we can only see 3 dimensions. But some people hypothesize, well, actually, there are more dimensions. Maybe Santa has figured this out. And all you need to do is to take these 1 billion presents, push them into one of these extra dimensions, and then you don't have to worry about anything in terms of the width or height or length of the sleigh, because they aren't inside those 3 dimensions, they're in a different dimension. So you just have to figure out a way of pushing those presents into the extra dimensions and then pulling them out one by one when you need them. Again, I don't know how, but maybe that's what he's doing. And it might be that there's rather more than just 3 dimensions. It might be there's 4, 5, 6. Some people think there are 11 dimensions. There are certain mathematicians who keep inventing dimensions more often than I change my socks. But that's always a possibility. But you might say, well, okay, maybe. But wouldn't all of this stuff that I've discussed so far, wouldn't that need a huge amount of energy? It's all very well saying, well, he can go really fast. And if he's made of the right stuff, he's not going to glow like a supernova. But if you really want to go fast and do all of these things in 36 hours, wouldn't you need a huge amount of energy in order to do that? Well, yes, the Santa himself, plus the sleigh, plus 1 billion presents, moving at what must be relativistic velocities at 1% of the speed of light, yes, that would take an incredible amount of energy. But we know, for instance, that black holes can power a ship, so why can't his sleigh be powered by a black hole? Again, a small black hole, a tiny little thing, smaller than a speck of dust, is enough to power a sleigh with all of the energy required that I've been describing. But if you don't like that idea, there's an alternative. And there's an alternative energy source that we're overlooking here. It's the elephant in the room. Santa goes round the world in 36 hours. And somehow he has to get an awful lot of energy to do that. The question is, the elephant in the room is, what happens to all the mince pies? No one is crazy enough to think he eats them all, surely. No, okay. Not every household will leave a mince pie for Santa, but even if only a small fraction of them do, that's an awful lot of mince pies. Remember, he's visiting 1 billion households or so. So what if Santa could convert all of the mass of the mince pies into energy? Einstein said you can. Einstein said this is possible. Einstein said the physics is perfectly well established. Mass and energy have an equivalence. If you have a certain amount of mass, in principle, you have a certain amount of energy, and vice versa. So we can work out if a certain number of households do give him a mince pie, assuming he only eats a tiny fraction of them, what if he could convert the remaining mass into energy? How much energy would he have available? Well, we can calculate it. I'm a physicist, that's what I do. A mince pie is 50 grams, roughly speaking. E equals mc squared, so take 50 grams and multiply it by the speed of light squared, you get 10 to the power 15 joules. I know that you're not familiar with the unit of joule. We'll come to that in just a second. But let's just finish by saying, how many households are we talking about? Let's assume that just a few percent of households leave a mince pie and 90-something% don't bother. They don't bother feeding the reindeer either. So if a few percent of households leave a mince pie for Santa, then a few percent of a billion is, let's say, for the sake of argument, 20 million mince pies, each of which has that much energy. So the total amount of energy that Santa has available to him over the course of the night is 10 to the power 23 joules. And you have no idea how big an energy that is. So let me convert that into something that you might be able to relate to. 10 to the power 23 joules is the energy output of a nuclear power station, not running overnight. It's the energy output of a nuclear power station running for 1,000,000 years. That is 10 to the power 23 joules. So Santa, if he can convert mince pies into energy, he has a huge amount of energy to deal with, and as I say, it is more than the output of a power station running for substantially more than that one evening. So he has more energy than he knows what to do with if he can do that. How do you extract E equals mc squared from a mince pie? Well, I don't know how to do it, but it doesn't mean Santa doesn't. One option is to take a mince pie and take an antimatter mince pie and collide them together in the large mince pie collider at CERN. That will give you all the necessary energy. It has the downside that A, you've got to find the anti-mince pies in the first place, and you've got to take them to CERN to collide them together. So it's not an ideal solution. Where do you get the anti-mince pies from in the first place? So, okay, maybe that's not sensible. But there is an alternative way to extract not all of the energy, but a surprisingly large fraction of the energy of any matter can be converted to energy in a very efficient way. Even more efficient than, for instance, our sun is fusing together atoms of hydrogen to make helium, and that fusion process has been powering our sun for billions of years. But there's a process that's even more efficient than that in terms of generating energy from mass, and that is you drop them into a black hole. So I know I've said black hole a few times, almost as often as I've said quantum mechanics, but if you do have a black hole and you drop matter into it, the process of the matter falling into the black hole generates huge amounts of energy. We think that quasars, which are the cores of certain galaxies that are visible across immense distances in the universe, quasars produce their energy because matter is falling in to a supermassive black hole at the center of the galaxy. We have a supermassive black hole at the center of our galaxy, the Milky Way. That's not actually having a lot of matter dropped into it, but we can see various places in the universe where matter falling into black holes generates enormous amounts of energy. I've actually photographed one of these quasars from my back garden. They are that bright, even though they're on the other side of the observable universe. It's still possible to photograph them with a camera because of the huge amount of energy that comes out of matter falling into a black hole. So it's definitely possible. How much energy could you release from a mince pie? I find it very difficult to find out. I cannot find any research papers of anybody that's working on this. So I think a reasonable fraction, we know that if you've got a very large black hole, you could convert as much as 10%, 20%, 30% of the total mass could be converted into energy. That's a huge fraction, bearing in mind how efficient stars are. They convert mass into energy at the rate of about 1%, not 10 or 20 or 30%. So it's definitely possible. So how can Santa actually do that? So all of these might be possibilities in the sense they don't break rules, but how can Santa manipulate space and time in the ways necessary to achieve all these things? Well, the bottom line is I don't know. But remember, who says Santa has to be human? It might be that Santa, well, no one's seen Santa, have they? So we don't actually know what he looks like. We just assume that he wears a red suit. Maybe he has a white beard, maybe he doesn't. And we just assume that he can't do the things we think he might be able to do just because we don't understand how he does them. So the bottom line is, how many laws of physics does Santa break? I would argue none. He does not break any laws of physics at all. We're pushing it as to how he does it. We don't understand the details, but nothing he does is absolutely 100% against what we understand for the laws of physics at the moment. So feel free to draw your own conclusions about the existence or otherwise of the portly, jolly fellow with the white beard and a penchant for wearing red suits. Regardless of your conclusion, I say once again, have a nice Christmas.